Class 11th Chemistry, Unit 4 Chemical Bonding in Molecular Structure, and in this video we will discuss about hybridization involving S and P orbitals. First come to Sp hybridization. It involves the mixing of one S and one P orbital, that is Pz, resulting in the formation of two equivalent Sp hybrid orbitals. These two Sp hybrid orbitals are oriented in opposite direction, forming an angle of 180 degree to give linear geometry, also known as diagonal hybridization. Okay, you can see this is one S orbital, this is one P, that is Pz orbital. When these two intermix, then they result these two Sp hybrid orbitals, and these Sp hybrid orbitals oriented in a linear way, and this bond angle is 180 degree. Okay, each Sp hybrid orbitals has 50% S character and 50% P character. Simply we can say in Sp total number of orbitals are 2. Out of 2, one is S orbital and one is P orbital. That's why 50% S character and 50% P character. For example, BeCl2. In ground state, the electronic configuration of beryllium is 1s2, 2s2. Now, in ground state, there is no half-filled orbital is there. Okay, that's why one of the electron from 2s is excited to 2p, and in excited state the electronic configuration of beryllium is this 1s2, 2s1, 2p1. Now these two orbitals of outermost state, that is 2s and 2p, undergo Sp hybridization and produce two Sp hybrid orbitals like this. Okay, now one Sp hybrid orbital overlap with half-filled Pz orbital of chlorine and make this sigma bond. Okay, as we know, chlorine, if you see the chlorine outermost electronic configuration is NS2, this is NP5. It is one of the P orbital is half-filled, and generally this is Pz. That's why this is Pz orbital of chlorine overlap with one of the Sp hybrid orbital of beryllium and form this sigma bond. In the same way, another Sp hybrid orbital of beryllium, this one, overlap with the Pz orbital of chlorine, this one, and form this sigma bond. And this geometry is linear, and you can also represent this structure like Be. This is Cl and this is Cl, and this angle is 180 degree. Okay, now come to Sp2 hybridization. It involves 1s and 2p orbitals to form three equivalent Sp2 hybridized orbitals, and these three Sp2 hybrid orbitals oriented in a trigonal planar arrangement at bond angle of 120 degree. Now let us see how can you draw these three Sp2 hybrid orbitals. This is 1, this one is 2, and this one is 3. Okay, now if we see the angle between these, this angle is 120, this is also 120, and this is also 120. And if you join these, then we will get trigonal planar or planar arrangement. Okay, now each Sp2 hybrid orbitals has 33.33% S character and 66.67% P character. For example, BeCl3 in ground state boron has electronic configuration 1s2, 2s2, 2p1. Now in the ground state there is only one half filled p orbital is there. But for the formation of BCl3 we require three half filled orbitals. That's why one of the electron from 2s is excited to the 2p orbital, and in excited state its electronic configuration is 1s2, 2s1, 2p y1, 2p, z1. Now these three orbitals, one is s and 2p orbital, undergo hybridization, and that hybridization is Sp2 hybridization, like this. This is one s orbital and these are the p orbitals, and produce three Sp2 hybrid orbitals which are equivalent in shape, and these three Sp2 hybrid orbitals arranged in a planar or trigonal planar arrangement. Now in case of BCl3, each Sp2 hybrid orbital like this one overlap with the p orbital of chlorine. This Sp2 of boron overlap with the p orbital of chlorine, and this form sigma bond. This is also sigma bond. In the same way, this Sp2 hybrid orbital of boron overlap with the p orbital of chlorine and form this sigma bond. Okay, and this you can also draw. This is B, this one is one bond, this is another bond, and this is three bond, this is chlorine, this one is chlorine, and this one is also chlorine, and this bond angle is 120, this is also 120, this is also 120. Okay, now next one is Sp3 hybridization. In this, one s orbital and three p orbitals mix to form four equivalent Sp3 hybridized orbitals, and these four Sp3 hybrid orbitals oriented in a tetrahedral arrangement at bond angle of 109.5 degree. There is 25% S character and 75% P character in each Sp3 hybrid orbital. Okay, take the example CH4. In ground state, electronic configuration of carbon, if we see outermost shell 2s2, 2p2, only two half-filled orbitals are there. But we require four half-filled orbitals. That's why one of the 2s electron will excite to 2p orbital, and in excited state its outermost electronic configuration becomes this. Now there is one s and these three p orbitals are half filled. They will undergo mixing and produce four Sp3 hybrid orbitals, and these four Sp3 hybrid orbitals arrange in a tetrahedral manner. This one is, and this bond angle is 109.5 degree. Again this is also 109.5, this is also 109.5, this is also 109.5. Okay, and in case of methane, each Sp3 hybrid orbital overlap with one s orbital of hydrogen forming sigma bond. Okay, this is Sp3 of carbon, this is one s of hydrogen, this is sigma bond. This is again Sp3 of carbon, this is one s of hydrogen, this is sigma bond. This in the same way, this is also sigma bond. Okay. Now come to structure of NH3 molecule. In ground state, outermost electronic configuration of nitrogen is 2s2, 2px1, 2py1, 2pz1. Now, in this case, no need for the excitement of electron. Okay, in the ground state, nitrogen will undergo Sp3 hybridization, and this Sp3 hybridization involves one full filled 2s orbital and three half filled p orbitals. Okay, one 2s and three 2p orbitals intermix and form four Sp3 hybrid orbitals. Three hybrid orbitals which contain unpaired electron overlap with one s orbitals of hydrogen atoms to form three nitrogen-hydrogen sigma bonds. and one of the sp3 hybrid orbital contains one lone pair of electron. Now see, this is a lone pair of electron, and these three, 1, 2 and 3 sp3 hybrid orbital of nitrogen overlap with the 1s orbital of hydrogen and form sigma bond. This is sigma bond, this is sigma bond, this is 1s of hydrogen, and this is sp3 of nitrogen. Okay, but in this case there is a lone pair of electron is there. Now we already know that there is a repulsion between lone pair bond pair is greater than bond pair bond pair. That's why the molecule thus gets distorted and the bond angle is reduced to 107 degree from 109.5 degree. This bond angle. This is less than normal tetrahedral bond angle. Why? Due to repulsion between this lone pair and these bond pair is greater than bond pair bond pair. And this geometry, this type of geometry is known as pyramidal geometry or distorted tetrahedral. That's why we can say NH3 molecule hybridization is sp3, but shape of the molecule or geometry of the molecule is pyramidal. Clear? Now come to structure of H2o molecule. Now in ground state, outermost electronic configuration of oxygen is 2s2, 2px2, 2py1 and 2pz1. Now again in this case, these two full filled orbital and these two half filled orbital undergo sp3 hybridization. Okay, and produce 4 sp3 hybrid orbital, and these sp3 hybrid orbitals oriented in a tetrahedral manner, and out of these 4 sp3 hybrid orbital, 2 contain 1 electron each and the other 2 contain a pair of electrons, that is lone pair of electrons. These 4 sp3 hybrid orbitals acquire a tetrahedral geometry with 2 corners occupied by hydrogen atoms while the other 2 by the lone pairs. Okay, now you can see this is oxygen. These are the 2 sp3 hybrid orbital occupied by lone pair of electron, and these 2 sp3 hybrid orbital which are singly occupied overlap with the 1s orbital of hydrogen atom and form sigma bond. Okay, that's why these are the 2 sigma bond and these are the 2 hybrid orbital containing lone pair of electron. Now again remember, hybridization is sp3, but due to the presence of these 2 lone pair of electron, its shape is bent shape. Okay, and again bond angle is smaller than normal tetrahedral bond angle. Now why? Because in this case there the 2 lone pair of electron is there. That's why lone pair repulsion is greater than lone pair bond pair, and that is greater than bond pair bond pair. That's why bond angle is reduced to 104.5 degree from 109.5 degree. And water molecule has V shape or angular geometry or bent shape. Okay, now again we have discussed the 3 molecules CH4, NH3 and H2O. In all these 3, central atom like carbon, nitrogen and oxygen has sp3 hybridization, but shape is different. This is tetrahedral, this is pyramidal and this is bent shape. Okay, now this is a regular because all are the 4 bond pairs are there, but in this case there is a 1 lone pair. That's why geometry becomes pyramidal. In this case 2 lone pairs electrons are there. That's why shape is bent shape. Now question arises, how can we find out the hybridization, hybrid state of central atom? And for this formula we again discussed. We already discussed. That is, number of hybrid orbital is equal to half of the number of valence electron in free atom plus number of monovalent surrounding atoms plus minus charge. Now all these 3 are neutral. That's why this is not required. Now let us see in case of water, oxygen. Okay, then you can say half of the number of valence electron in free atom of when oxygen is free, that is 6, plus monovalent surrounding atom These are the hydrogen is the surrounding atom and they are the two hydrogen atoms. That's why 6 plus 2 divided by 2, that is 4. That's why we can say there are 4 hybrid orbitals, and when hybrid orbitals are 4, then hybridization is sp3, but 2 are lone pair of electrons. How we can say, actually it is surrounded by the 2 hydrogen atoms. That's why bond pair electrons are only 2, and that's why 2 lone pair of electrons. That's why geometry becomes bend shape. In the same case, we can also determine hybrid state of nitrogen in NH3. Okay. Thank you. Subscribe my channel to get the new videos. In the next video, we will discuss the hybridization involving S, P and D orbitals.